Okay, yeah, we're a little bit early, so don't worry. We're just going to talk about the exam for a couple minutes. So there, you should have seen the grades for the exam come in. And there's going to be one grade, which is the raw score, which is going to be in the online version column. And you'll see the online version column has changed names and is turned to 0 points. That's because I want to have it all in one column, so I only have one or the other, not both. So what we'll see here is that all of the grades, in fact, this class is the only one that doesn't have, I think 4. Quiz 4 might not be. But I think I have all the other grades up to the exam, and I'll have quiz 4 done soon. So that is good news for me. I'm kind of caught up. But it also, there was a 13-point curve. Those of you who came and took it in person, I will give your exams back on Monday. I still have 2 people trying to take it online before, because the COVID symptoms have kind of gone away, so they can take it this week. And so I will hand them back on Monday, and then you can go over them. You can go over what you got right and wrong. And there were scores above 100. So somebody did make a perfect 100 on the entire exam. So they got to 113. So number one, it's possible. And I figured out the 2 questions most missed by everybody. So I'm going to talk about those later, but not today. Okay, we're starting here. It's 2 o'clock now. I'm going to go ahead and start with the main lecture here. And so where we left off last time was our bicyclo nomenclature for chapter 4. Our next quiz next Wednesday will be over the end of chapter 4 and chapter 5 only. Okay, so I should get through chapter 4 and 5 before our next quiz. So that'll be where we should be back on track for our next exam. We are slightly behind, but I think we can make it up. Okay. So what I would like to do is I'd like to go ahead and continue on with our nomenclature system here. So I've been playing in my Apple Pencil, so I might be faster. We'll see. Okay, so let's review our rules up to now. Up to now, I said that we start with looking at the longest parent chain of carbons, but then I told you to go to that resource on Canvas. The number 1 rule there actually is to assign the functional group with the highest priority. So now we have to actually use that rule, okay? So in this case here, alcohol ranks above alkanes, and therefore it is the functional group here. So that means we have to name it for the alcohol, and that means it changes a couple of the rules. It doesn't supersede them, it changes what you look for. Okay, so the first thing we need to look for, if there's a functional group, is you need to find the longest parent chain that contains that functional group. Okay, so, well, you have this right here. You could say, well, does that mean that I go, oh, here's my OH, so I have to go this way and only have 4 carbons? No, it doesn't have to be a continuous chain using the functional group in the case of an alcohol, but it has to be on the longest chain. What that means is our longest chain is actually this one right here. 1, 2, 3, 4, 5, and 6. So now we have 6, which is hexa. We have an alcohol, which changes the E at the end to an OL. So it's hexanol. Yeah, hexanol. It's hexanol. Yeah. All right, so that's, oops. Hexanol. Okay, but where is the alcohol? We have to signify where the alcohol is. Now, we need to figure out whether we're going to number it from one side or the other. So we could do 1, 2, 3, 4, 5, 6. And that would give us our alkyl substituent as the lowest number. But we're naming it for the alcohol. So you want the functional group it's being named for at the lowest number possible. So that means we can't use these right here. We must use the numbers here. So now that we're using those numbers there, that puts us at the 3 hexanol. So it's at the 1, 2, 3. It doesn't have to be on number 1 anymore, okay? It doesn't have to be the lowest number. It has to be the fact that you change the end of the word, that has to be the lowest number, okay? So now that we have that, all we have to do is that locate our substituents here, and our substituents on the 5, and it's a methyl substituent. So our final name is 5-methyl-3-hexanol. Okay, now there is another way to do the location of the alcohol to even make it closer to where the alcohol is. What we can do is we can, instead of doing the 3 here, we can say 5-methyl-hex-A-3-hexane-3-ol. So that's the 3 is right in front of the functional group. Just like it is in a substituent here, except we're telling us where that functional group is. We're going to use that rule again in another way of naming these things, okay? So just keep in track of that. Okay. So again, we find the longest main chain with the alcohol or the highest priority group on here, which is an alcohol. We number the alcohol as the lowest number possible. Substituents, number them, alphabetize them, put it all together. All right, questions? Okay, so let's do cyclic alcohols. So when we had just anything on a cyclic ring, right here, we said that was the 1 position, right? So if we have an OH, that's also the 1 position. And it doesn't matter what other substituent we have, as long as it's not a higher priority functional group, we know exactly where to start numbering from 1. Because this is going to be our 1 position, our 2 position, and our 3 position. Okay, so let's put that all together. So we have 1-cyclopentanol, right? 1-cyclopentanol. We have the cyclopentane, drop the E, add the OL, 1-cyclopentanol. And we have the 3-methyl. Let's see if I can squeeze it in there. Yeah. Okay. Is that 1 required? No, because it has to be that number 1 slot. So we could drop the 1, we could put the 1 over here, or we can put the 1 where it is. Okay. We just have to make sure where we keep hyphens and such. Okay. Questions on that? Yes.
So like a chart for like priority of functional groups?
Yes. If you look on the last page of the nomenclature review on Canvas, the last page has every functional group. You will go through all of organic chemistry. It has the priority. They're listed in priority from lowest to highest. So lowest priority is going to be like phenyl groups, halogens, nitro groups. Those don't change the name. Those are always substituents. Ethers, boom, always substituents. Then we have alkanes, alkenes, alkynes. Those kind of change the name a little bit. And then alcohol is our amines and then alcohols. And so that list is in there. Yes. All right. So let's see. So that means that if we had something like this here, hang on. I'm on the wrong example here. There we go. If we had something like this, and let's put an OH here, a methyl group here, and then 2 methyl groups down here. Yes.
You said that the 1 isn't required. Are you just saying like it's not required to be there? Or
It's not required here because if you're in a cyclic group, you don't have to denote where 1 is. 1 is the function, whatever the functional group is.
you could just ignore the 1.
You could just ignore the 1. But I love to always have the 1 in there just to make sure that number 1, we paid attention where the functional group is and that we started numbering it correctly. Okay, it's not required, but definitely good to have. Okay, so let's start here. Now, traditionally, we would think, okay, well, we have a couple ways to number this. We know this has to be 1. Okay, and we have 2 groups down here. Okay. And that would give us 1, 2, 3, 4, 5, 6. That would give us 3, 6 for our substituents, right? Let's go around the other way. Let's start at 1 here, 2, 3, 4, 5. So our substituents are on the 2 position and the 5 position, right? So 2 is less than 3. So we're going to number this one counterclockwise, where we numbered the other one counterclockwise as well. But so what we're going to end up with is 2, 5, 5 dash tri methyl, because we get to aggregate all the substituents that are the same kind together. Then we're going to do cyclohexanol. Okay, and again, we could 1-1 here, cyclohexanol. But again, the 1 is not required because it has to be that position. That only works with cyclos, by the way. So we'll only do it with cyclos. Okay. Questions on that? Yes.
What if there are 2 alcohols on the same?
What if there are 2 alcohols on the same one? That's a great question. What you're going to do, we actually have a slide for that. Hold on. Okay. We do have a rule for that. And so I want to do that. But before we get to that rule, let's go ahead and take a roll. Let's see, we have how many people online? 16, including me. So 15 people online. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14. So 30 out of 50 live. That's not bad, considering the weather. Okay, everybody got that? So now I want to talk about common names. Okay, so we had those common names for alkanes, right? And we had substituent name for alkanes, right? So if it was whatever the number of carbons was plus YL at the end, it was a substituent. So we have those common names, butyl, isopropyl, sec-butyl, those kind of common names. That's how we use common names for naming alcohols. What we do is we take the common name we'd have, like in this case here, in IUPAC, we would say this is 1, 2, 3 carbons. So, and this is the 1 and the 2. So this would give us 2 propanol, 2 propanol. Okay, that would be the IUPAC name. But doesn't that alkyl group look like something? Doesn't it? If we put a little squiggly line right here, doesn't it look like the isopropyl group? Well, that's how we're going to name it in the common name. We'll say isopropyl space alcohol. Oops. Erase. All right. Let's see. Alcohol. That's an O at the end there. Okay. So that's how we would name it. So if we just had a methyl group, it'd be methyl alcohol. Ethyl group, ethyl alcohol. If we had a sec-butyl group, that's one too many. 2. Working on this. I have to double tap to get it to do erase. Okay, so this looks kind of like the sec-butyl group, right? If we drew the squiggly line right here. So that makes this alcohol, sec-butyl alcohol. So we do sec-butyl space alcohol. So you can really tell common names from IUPAC names because common names typically are going to have a substituent name to them, a YL in them, and a space. Okay. In our other IUPAC words, they all string together or they have hyphens or commas. So we have to look for those kind of things to separate the difference between a common name and an IUPAC. Okay, so what about more than one alcohol on anything? So what we get to do is we get to, at this point, say, okay, what did we do with multiple substituents? We added mono, di, and tri, right? We're going to do the same thing for multiple of the same functional group. Okay, and so for this right here, we have 2 carbons. So that would be ethane, right? And we're going to have to number one of them 1 and one of them 2. I don't see a way to, any other way to number that. You can number them the other way, but it's going to get the same number. So we're going to end up with 1, 2 dash. Let's see, 1, 2, ethane, diol. So the numbers are required because you have to show that one of the alcohols is on the 1 and one's on the 2. And you could even go crazy. Oops, no. OH, OH, OH. So we have 1, 2, 3, 4, 5. So we have pentane, triol, and it's symmetrical. So we're going to go 1, 2, 3, 4, 5. So we have 1, 3, 5 pentane triol. TROL. What? Try. That's a. Oh gosh, it keeps looking like an H. Let me try one more time. Try. Come on, one more. That's my last try. Try all. Okay, so we see the rule on there. We just have to make sure we designate where each of the alcohols is and the number we have. Okay. And so when these have, these are the IUPAC names, but some of these have really common names. This one is actually called ethylene glycol. Okay, anybody heard of ethylene glycol? Two things you should know about ethylene glycol. It's the antifreeze in your car. And number 2, it's a very sweet taste to cats and it kills them. So don't leave it out. So what they're doing for that is they're actually starting to replace it with propylene glycol, 1,3-propylene glycol, which is less toxic to cats, but still performs the same duty in their antifreeze. So if you have a choice, get the propylene glycol. Okay. Questions on that? Yes.
On the one on the right, you numbered it 1, 2, 3, 4, 5. How come on the left you only did 1 and 2? Like, how come it's not?
There's only 2 carbons. Those are the other 2 are oxygens. See, this is a carbon. We only number the carbons. We don't number the other atoms because we need the longest parent carbon chain. Got it? All right. So that being said, all right, any questions on alcohols or cyclic alcohols or diols and trials? Okay, so what we're going to do now is we're going to change slightly. We're going to change what I call the infix. I said that if we only have carbon-carbon bonds that are single, that was an ANE. And the E signified it was a hydrocarbon at the end. We took that E off and added OL when it turned into alcohols, right? So let's look a little bit closer into alkenes first, and then we're going to see about mixing the 2 together. So if we're going to go for a double bond, that's going to be anything with an EN and something else at the end. Anything with a triple bond is going to be a YN. So those are those 3 kinds of hydrocarbons: alkane, alkene, and an alkyne. But now we have those things plus additional functional groups. That's what we're going to learn how to name today. So let's go about naming our alkenes. So obviously we have to include the ENE section of it right here, but we have some rules. The rule is, you want to get the longest parent chain, but you are required to use both carbons of the alkene. For example, if you had something, oops. Come on. If you had a hydrocarbon that looked like this, you can't say, oh, well, the longest parent chain is this one right here, because it doesn't contain both carbons of the double bond. It has to contain both carbons of the double bond. So in this example here, if we blow it up, we can do, let's see, 1, 2, that's a methyl group over here, a methyl group over here. So that's probably our longest chain, right? We should get better at recognizing our where to start from our chains too. Now, the other rule is that now that we have 1, 2, 3, 4, 5, 6 carbons there, now we have hexene, E-N-E, hexene. But where is the double bond? Is it between the 1,2 carbon, the 2,3 carbon, the 3,4 carbon, the 4,5 carbon? We don't know. So what we need to do is just need to write the number of where the alkene begins. So in this case here, we're going to number from this side 1, 2, 3, because the alkene will have the lower number. If we numbered from the other side, the alkene would have the higher number. Okay, so this is going to make it 2-hexene. You only have to label the first carbon of the double bond, but the parent chain has to go through both carbons of the double bond. Okay, and then now that we already know our numbering system, because we have less ambiguity than in the hydrocarbons, we know it has to start in this way. We can start numbering for our 3, 4 methyl groups. And I see a 2-methyl group, a 3-methyl group, and a 5-methyl group. So that's going to bring our full name to 2, 3, 5 dash tri-methyl, sorry, that's the R, methyl. Let's see, no space, dash 2 dash hexene. Okay. And again, both of those have to be in there. When we have a group like this, we actually have a special name for that in our common names, and I'll talk to you about that in a slide or two.
So
Yes.
why wouldn't you continue the numbering to the 6th carbon? And so you could dimethyl. And so that would.
But one of these methyl groups has to be on the longest chain, this one or this one.
Oh, I see. Never mind.
And one of these methyl groups has to be on the longest chain, either one. You can number it differently as long as you chose, you know, this methyl group and this methyl group, you should still get 6.
Right.
And you still should get the alkene on number 2. So that I think, you know,
Yeah.
you have choices, but the numbers still end up the same. Okay, so let's see. All right, so find the alkene in the parent chain. Both carbons must be there. Assign the alkene the lowest number and add your substituents, alphabetize numbers, string it all together. All right, questions? Okay, so there are a couple things we need to know about this. Again, if we have a choice, we can't do saying, well, you know, gosh, I would get 2 more carbons if I'd get 1 more carbon if I did this. Here, can't do that. Both carbons must be there, okay? And the other cool thing that we have with alkenes is we have that cis-trans isomerization. And I know we talked about this already when we were talking about dipole moments and stuff. So every alkene, if it has more than one substituent, can have isomerization, stereoisomers. If it only has 2 things attached to its double bond, we can call it cis and trans. One of them has to be attached to one carbon, one of them has to be attached to the other carbon. If they're both on the same side of that, if you drew an imaginary line, they're both on the same side, that's our cis isomer. And if they're on opposite sides, one here and one here, we call that our trans isomer. And again, those are lowercase. And those will front at the beginning of the word. So let's go back to here. We actually have 1, 2, 3, 4 things attached to this alkene. So we cannot call it a cis or trans isomer. Okay, questions on that? Okay, the next rule is, okay, the ene is all about double bonds, and the all is all about the functional bonds. What if you have both? Well, there's a weird rule because the alcohol is like the first functional group and it's kind of almost there with the alkene. We still have to say both of them are there and we have to show where both of them are. Okay, so for example, right here, we have an alkene and we have an alcohol. The alcohol is at the end of the word. It's going to take priority. It's going to be where you're going to number from. So our longest chain is 1, 2, 3. So we have propene, but we don't really have propene because we have an alcohol. So we drop the E. Go P, and then 1 all. And then we have to locate the alkene. The first one of the alkene is 2. So we have 2-propene-1-all. I told you one of the ways we could identify it before was to put the 1 in front of the all. This is where you have to put the 1 in front of the all. The 2 in front of the propene tells you that's where the double bond is. The 1 in front of the all tells you where the alcohol is. And yes, alcohol is at the end, so it takes priority and it's where number 1 is. All right, questions on that? So we could even go crazy and go with a much longer molecule. Right here. And notice our functional group is not at the end of the chain, but our alkene is. Which do we name it for, the alkene or the functional group? The functional group. So we have to number it from this side. 1, 2, 3, 4, 5, 6. So our new name is going to be, let's see, the 6. And then of course we have to have 7 down here because it has to contain the double bond to get to the ene. So we have peptine, and it starts on the 6. So we have 6 heptene dash 2 all, because it's on the number 2 carbon. And then of course we have a substituent right here on the 6 carbon. So we have 6 methyl, 6 heptene dash 2 dash all. Okay, not breaking any rules. We're just adding a couple, looking at priority as a function. Okay, questions on that?
If we're going the other direction, say we have the name and we have the drawing.
Yeah.
The double bond always goes from like the 6 to 7 or like 3 to 4.
Right, it's whatever the lowest number is the first carbon of the double bond, and then the next higher number is the next higher, is the next one. So if you started on 2, the double bond will be on carbon 2 and 3. If you started on 7, it'd be 7 and 5, 7 and 8. So it'd always be the next one. Okay, so we have also kind of a way to do things at, you want to ask me about what do you do if you have 2 double bonds? Plant in a thing. So what we do for double bonds, if you have more than one of them, is you do the exact same thing we do with diols, where you say diene, triene, tetraene. So if we had this structure here, we would say, okay, actually, let's make it hard there. Okay, so we have 1, 2, 3, 4, 5, 6, 7 carbons. Are we going to label this from the left or the right? Left, because we're going to start with the lowest number here on the first carbon. So we have 1, 2, 3, 4, 5, 6, and 7. So you have heptatriene. So we got to do heptatriene. Heptatriene. So that identifies the fact that we have 3 double bonds and 7 carbons, but we have to locate them all. We have to do 1 comma, 3 comma, 5 dash heptatriene. Okay, do we see how that works? It's kind of just like the alcohols. It's just we're doing it with alkenes instead. We just have to make sure to go the first carbon of each double bond is the number we use. Okay. Let's see. Okay, so that'll work with trienes. What do we do for cyclic compounds? Okay, so let's do, well, let's start there. Okay, so here it's just like every other cyclo. It starts with the functional group. So we have cyclopentane, cyclopentene, right? So cyclopentene, okay? And I'm going to number it 1, 2. Why are those 1 and 2? You got to start somewhere on a ring, and then the next carbon has to be the double bonded one. So that's why they're 1 and 2, okay? And because it's ambiguous to see which one of these is 1 and 2, if I drew a different compound and put a methyl group there, that makes this the one carbon. Now it's one methyl cyclopentene. Okay,
So you know where to start because it's like right next to the double bond.
it's because you have a substituent and the double bond can both be on one. You use that as one. Okay, so you wouldn't want to start labeling here because then your substituent's on two. And because you can choose either one of those carbons, you'll choose the one where the substituent's on the lowest one. So let's see. Let's erase that one. So let's see, then let's name that one. Okay, so because we're starting from here, because that's our lowest number, 2, 3. So we're going to have 1, 3 dash dimethyl dash 1 dash cyclopentene. One. And of course, the one is not required, but it is always good to see. All right. So let's do one more of those cyclos. And let's go from the simple one to something a little different. Okay. So we have 7 carbons. So it's cycloheptene, and we have a substituent here. Now, if we started labeling here, we could call it 1, but can we do that? Can we start labeling here as 1? We have to start here because we have to have 1 and 2 go through the double bond, which makes our substituent number 3. Right here. So we're going to have that is going to be 3-methyl cycloheptene. 3-methyl cycloheptene. Nope, no dash there. Cycloheptene. All right, questions on naming rings? Okay, so just like with the alcohols, we have common names for the alkenes as well. So the one thing that we have for them is we basically count the number of the carbons you have, treat it as a substituent, and add ene on the end of it. So in the case of systematic here, we have F-ene, right? So that's IUPAC. But what we'll do is we'll say ethyl-ene. So it's just like we did with alcohols, substituent name. Yeah. Wait, hold it. That's isobutylene. Isobutylene. So it's looking like whatever your thing is. So that's anyway. So that's easy to remember. And so again, propene would be 3 carbons, propyl group, ene, propylene. So it's neat that the common names use a system as well for most of the time too. Okay, so let's see. What else? Other example do I have here? Oh, now what we do have is a couple special names for parts of alkenes. So I said before, when you have an alkene that does this, that's an H, right here. If it's outside of, if it's at the end like that, we call that a methylene. Why is it called a methylene? Okay, well, it has 1 carbon and it has a double bond. So if we put the little squiggle mark in between the other carbon and that, 1 carbon double bond, methylene. So it's called the methylene group. Okay, unfortunately, that's not true for if we have, oh, actually, I'm going to do it in, let me do it in stick figure. So in stick figure, that would just look like that with the squiggle mark here. So if we had a group that's just that, and then there's squiggle mark here, you would say, well, gosh, that's the ethylene group, right? Well, no, we already have ethylene. So we actually call this the vinyl group. Okay, so because we already used ethylene up here. So we have to call it something else. So it's called the vinyl group. So it's looking like an ethylene attached to some other substrate. Okay, and so then that's kind of cool. Well, we also have another one. Whereas if we add one more CH2, we call this the allele. And I would put those on your chart with all the other alkyl groups because that's how things are named. When we add a chloride to this, it's called vinyl chloride. When we add an alcohol to this, it's allele alcohol. So these are substituent names just like other things. It's just they're unique to alkenes, which is why we didn't learn them until now. Okay, so methylene, 1 carbon, vinyl, 2 carbons, allele, 3 carbons. And then it follows pretty much the system after that. Okay, questions on that? Okay, now we're going to move to alkynes. Okay, and alkynes are the same as alkenes, but because it tells us something about the carbon-carbon double and triple bonds, we have to use both names to locate them. So let's go ahead and talk about it. So it follows all the other rules that we had before. You have to find both carbons of the alkyne in the longest paired chain. You're trying to locate it at the smallest number. You do all the same rules here, okay? And if you have more than one, you do the same rules again. Di-ine, tri-ine. So we can actually end up with some crazy structures like right here, but we know how to name it, right? Because we're going to say we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. So it's octane, but we have 2 alkynes, octane, octadiene. So octadiene, okay? We have to locate where they are. Luckily, it's symmetrical, so it's 1, 2, 3, or 1, 2, 3. So that means it's 1, 2, 3, 4, 5. One of them starts on the 3, one of them starts on the 5. So we can do 3, 5 octadiene. But we still have 2 more carbons, which are methyl groups. And so this is the 5, 6, 7. And so we have to add to the front is 2, 7 dash dimethyl dash 3, 5 octadiene. Octadiene. Okay. Questions on that? So that's pretty cool that it's, you know, nice and symmetrical. Let's see. Now there are opportunities that when you can have a double bond and a triple bond in the same structure. Okay. Which one takes priority? Alkene is just slightly more commonly used than an alkyne, so alkene takes the priority. So if we're going to number this, we're going to number it from this side: 1, 2, 3, 4, 5, 6, 7. Okay. And it's probably the only one that breaks the, if it's last, it's highest priority rule. Because we're going to have to call this an ene, and we're going to have to call this an ine. So if we're going to do this, we have to, let's see, we have our alkene starting on the number 2 carbon, our alkyne starting on the number 5 carbon. So we're going to start with, let me change colors here. So we have 2 dash heptene dash 5 ine. So We like to call the "een all" rule because "een" comes first, all. I call this the "een ein" rule because the "een" comes first. And because the "een" comes first in this one, it actually has priority. Are we done naming this compound? I think we have isomerization. Don't we have isomerization on there? We have a group on this side and a group on this side. If we draw that line here, what isomer is it? Cis. So we're not done yet until we add cis. So our full name is cis-2-heptene-5-ine. You know exactly where the alkyne is, exactly where the alkene is, exactly the configuration of the double bond. Precision. It's like a BMW. Precision. All right. Questions on alkenes, alkanes, and alkynes, and alcohols. Okay, so now we're going to talk about alkyl halides. Okay, now the cool thing about alkyl halides is they don't change the name. They're always a substituent. So we just name the parent hydrocarbon, whatever it is, and add it to the system. Okay, so basically you're just going to give whichever substituent is the lowest number, the lowest number. Chloride is not special. It's always a substituent. Things that are always substituents are halogens, nitro groups, ethers, and phenyl rings, unless it has a special name. And so these are always just substituents, and you would just lowest number your substituents. In this case here, 1, 2, 3, 4, 5, 6, 7. And so we have a substituent on 2 and a substituent on 5 on this one. If we numbered it from the other side, it would be 1, 2, 3. Our first substituent would be on 3. Okay, now we follow all the oral rules. Chloro comes before methyl in the alphabet. So our name is going to be, let's see, chloro is first. So 2-chloro dash 3-methyl. No space, heptane. There's no double bonds or anything like that. Okay, so again, we're going to try to get our substituents. Halogens are not special, they are just substituents. So if you have a mixture of ethers and nitro groups and methyl groups and alkyl groups and halogens, lowest number. All right, questions on that? Well, they also have common names. So, and the common names luckily form the rules we've used so far. The alkyl substituent it's attached to, and then add whatever halogen it is, okay? And there's, of course, a space between them. So if we were to, let's see, let's draw a fancy one and a not so fancy one. Right here, we can name all these in their common names by looking at what the substituent is. This is tert-butyl, right? So it's tert-butyl. And then space iodide. Okay. And then we have this one right here. This is sec-butyl. There's more isomers, butyl, space, bromide, no capitalized. And then this one would just be ethyl chloride. Oops. Okay, so we have that nice nomenclature there. And if they're more complex than that, we can't just use a common name, it'll have an IUPAC. But if you can see the alkyl group, recognize those alkyl groups, and now those 3 vinyl groups you have to remember, methylene, vinyl, and allyl, then you'll be able to do that system. Speaking of vinyl, one of the more common ones is this one right here, vinyl chloride. So why is it so special? Well, it turns out vinyl chloride can react with itself very vigorously to create a polymer right here. And basically that's just, it adds to itself over and over and over and over again. And we'll talk about this in chapter 10. But this is called vinyl chloride. And this is polyvinyl chloride. Anybody ever heard of polyvinyl chloride or PVC? That white pipe at Home Depot? Well, it's made out of that. It's also the clear tubes that come out of beer kegs that have plasticizers in them. So PVC is very useful industrially because it can be very rigid or it can be very flexible. Okay. So that's vinyl chloride. And so that's named that way. That's kind of cool. And one of the other things we can do is if we put 4 fluorines on here, we call this tetrafluoroethylene. And if we do the same thing where we make a polymer out of it, it's called polytetrafluoroethylene, or PTFE, or trade name is Teflon. So Teflon's that white heavy plastic that nothing sticks to. The reason nothing sticks to it is because of those fluorine carbon bonds are so strong, nothing wants to react with it. And so it's a very inert material. So it's a very good thing to have. All right, let's do a couple other common ones. So if we had CH2Cl2, this one's going to be methylene chloride. Okay, you'd say, but it also goes by dichloromethane. That's what the UPAC name would be, 1,1-dichloromethane, or the common name is methylene chloride. And it's used as a solvent, and so that's why it's really common. Now, if we take one of those hydrogens off and do HCl3, that has a common name too, that's harder. It's called chloroform. They see old spy movies where they hold the little thing over somebody's mouth and they kind of pass out instantly. It takes a really long time. Don't do it. Anyway, it's one of those, but that's the name there. So it's just movie magic. It's like crashes don't sound like that. Yes.
For the methylene chloride, so the common name, you wouldn't say methylene dichloride. It would just be chloride.
It would just be methylene chloride or dichloromethane.
Okay.
Yeah. And then we have another one that we can do is CCl4. And we call that either, this would be tetrachloromethane under our UPAC names, but we call it carbon tetrachloride. Tetrachloride. Okay, so we don't have a methylene with 2 hydrogens on it anymore. We don't have a 1 hydrogen there, so we call it carbon. There's no carbon hydrogen bond, so it's carbon tetrachloride. So technically this solvent is an inorganic compound. Ooh. All right, any questions there? Okay, so that's the naming for what we're going to do for the next couple chapters. All the way through chapter 7, we're going to use the alcohols, the alkenes, the alkynes, and the alkyl halides in our reactions. So that's why we have to name them now, okay? So now I'd like to go and switch gears a little bit and go to different ways that we can have chains of carbon molecules in what their different configurations can be. So the cool thing is that when we draw these things, we draw them out like this, and that's kind of the skeletal structure. It's kind of how we do it. But remember that, and write this down, sigma bonds can rotate. Pi bonds can't rotate. Sigma bonds can rotate. Okay. So that means, if you had a compound, you said, oh, well, this atom right here, I've labeled it. I know which one it is. And just sitting there while you're looking at it, it's just going to slowly start rotating around one way and then the other and the other one way. Just going to keep moving because there is only a very low barrier of energy to keep it from moving around, okay? So I'll talk about that. Now, if it rotates around such that you can see one so that they're together like this. If we looked at it on end, here, we would see that this one right here has all of the hydrogens lined up. And we call the angle between the hydrogen on one, let me change to red here, one atom here through the carbon, through these, we call the angle difference in those 4 carbons, what we call that is dihedral angle, okay? So if they're spread out really far like this, we actually have, this is the dihedral angle. We practice on this one here. And then this is the dihedral angle on this one here. It actually goes down, goes through these carbons and goes back up to this hydrogen there. So when they're overlapping like this, we call it a 0 dihedral angle, okay? Because the 2 groups are lined up on each other. And if you notice, all of the groups are lined up on each other because they want to be at that 109.5 degrees. And well, there's the other 109.5 degrees going back into the other carbon. So that's why it looks like they're that far apart. Now, if we have this dihedral angle shown here, that's as far as they can get spread apart, right? So that might be our lowest energy conformation. Yes, question.
So is the dihedral angle, is that the one where like you can't see the carbons behind it and you're looking at it like this?
Correct. What we're looking at is, if my thumbs are the 2 carbons, we're looking through the thumbs and we're looking at the angle that the 2 substituents on those 2 carbons are.
Okay, so it's lined up and that's like.
So yeah, if they line up like that, that's 0 dihedral angle. And if they tilt like that, that's some dihedral. And the biggest dihedral angle we can get, because we have 4 things bonded to carbon, is 60 degrees. Okay, so that's one way to look at it. And so we have words for the different conformations instead of having to draw them out. When they overlap together and have 0 dihedral angle, we call that the eclipsed conformation, eclipsed. Think of it as one atom is going in front of the other one. And so you can't see it. It's more like an eclipse of the sun. Now, in the other one, they're in between, as close to in between as the other 2 atoms as possible. We call that staggered. So we have staggered configuration and eclipse configuration. Okay. So I want to talk a little bit more about staggered and eclipsed and look at their going from one to the other, okay? So if we had these, and I want to take a look at the different sets here, we're going to start with looking at just this atom and just this atom here. Right now, if we were to look down this carbon-carbon bond, we would see that they are 60 degrees apart. Okay, but there's a sigma bond, it can rotate. So what if it rotated 60 degrees, and we're going to rotate only the back 60 degrees. We have to keep one of them stationary. We're going to rotate the back 60 degrees. What happens? We get a 0 dihedral angle on those 2 atoms. We started at 60 over here degrees, and we ended up eclipsed by going 60-degree rotation. Okay, but if it keeps rotating, it's going to now be in a staggered configuration, but it's a different staggered configuration. Notice that this atom is now on the relative left side of the molecule. Excuse me. Must have some cat hair in my mask. Okay, so we're now at a different staggered configuration, right? Because the back sphere is on the relative left side. And we can keep doing that. We can keep going around. So we can have multiple configurations, 60 degrees, 60 degrees, 60 degrees, 60 degrees. So we need to start looking at that and how we can use that to our advantage. So the way that it's kind of hard to draw all the different spheres and label them all different ways. And so what we're going to do is we're going to come up with a faster way to do our drawing so we can figure out whether we're eclipsed or figure out whether we're staggered, okay? So what we're going to do is we're going to draw these things called Newman projections, okay? So in this case here, we're starting with a staggered configuration right here. And we rotated this side 60 degrees in this direction. So basically we did the same thing here. We're going to rotate this hydrogen 60 degrees. And see how it's kind of cleaner, easier to draw? And I'm going to teach you how to draw these. Yes.
So for the staggers, the left and the right, you would just, there's not like a different name for them. You would just go call them staggers.
They're staggered. We will have different names for them in a little bit, but right now they're all hydrogen. So it's just staggered and eclipsed. When we change their identity, we have different names. Okay, good. You guys are thinking ahead. This is great. Okay, so then if we do another 60 degrees right here, we now have this here. So it's easier for us to tell where the different atoms are. So that's why we're going to use the Newman projections to work on that. So how do we draw a Newman projection? Okay, so what you need to do is you need to figure out what two carbons you want to look at. Okay, so you're going to get perspective view. And you're going to say, oh, I'm going to look down these two carbons. And if I look down those two carbons, what I'm going to see is, oh, look, I got a hydrogen up here. I have a hydrogen in the back, and I have a hydrogen on my left and a hydrogen on my right. Okay. So the way we're going to represent that is we're going to say, okay, the carbon I see first right here is going to be a dot. Okay. And the carbon that's behind it is a circle. Okay. And then what we're going to do is we're going to draw with this same perspective right here, all the things that are attached to those two carbons. Okay. So again, we're going to start with the first one first. And it's going to start with the center carbon. We're going to have that. And then we're going to have a hydrogen up, a hydrogen to the left, and a hydrogen to the right. Okay, if we go back and look at that structure here. So we have a hydrogen up, a hydrogen to the left, and a hydrogen to the right. But if we're looking here again, we now have a hydrogen up and to the left. We have a hydrogen up and to the right. And we have a hydrogen pointing straight down. See the little wedges here? So we need to draw a hydrogen here, and a hydrogen here. So the ones on the propeller here on the front, the ones on the tire swing here are on the back. Okay, so it's all about how you're looking down this sight line here. This hydrogen is in the plane. These two carbons are in the plane. This hydrogen is in the plane. Hydrogen in the plane, bonded to carbon in the plane, bonded to this hydrogen down here. So it's all about being able to get that first vision right. Once you get that first vision right, we can start rotating things. Okay, so that's going to give us our setup. So let's do this with something simple like ethane. Okay, so we're going to draw ethane in a three-dimensional structure. Okay, we're going to do right here. Let's draw the ethane with black here. So we're going to do dash, 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 hydrogen, wedge out here, hydrogen, and hydrogen down. Notice that I put the one in the plane down this time. So we're going to have a slightly different picture. And then this one's going to be up here, and then dash, 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 hydrogen, and then wedge out here, hydrogen. So our perspective, again, we're going to start looking down this direction right here. So we're going to put our thing in the middle here. And one of the hydrogens is up and to the left. One of the hydrogens is up and to the right. So we're going to draw those. Hydrogen, hydrogen, and then one is straight down. And if we're continuing looking down the thing, our next carbon here, drawn by the ring, has the hydrogen up, hydrogen over here, and a hydrogen down. Okay, so that's cool. That means that we have these two hydrogens. And what kind of structure do we have? Eclipsed or staggered? Staggered, okay, great. So if we were to draw this as an eclipsed, all we have to do is rotate this by 60 degrees. And so then we'll have hydrogens all lining up, right here, and this would give us our position. So if we were to redraw that in this configuration, it would look like we would have the straight hydrogen up, 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 hydrogen back. Notice that the hydrogens that are back and up are on the bottom now. And that gives us this. So the difference, the pushing away of hydrogens are what we call, so which do you think is higher in energy? One where they're a 0 dihedral angle and closer together, or at 60 degrees staggered and further apart? 60 degrees and further apart, because those hydrogens are not little dots in space, right? There's those clouds of electrons. And so as the clouds of electrons come near each other, they repulse each other. So you want them as far away from as possible without breaking any bonds. So the staggered configuration is the lowest energy configuration. Okay, but then you say, well, then there's a barrier to do this. Well, it's not very high, so we can rotate that sigma bond. Okay, so we have that rotation, and then we have differences in energy. So now let's talk about the differences in energy. Let's start with that high energy state we started out with here. And we see that we have hydrogen butting up against hydrogen, and we have 3 of those because we have 3 different hydrogens. Okay. If we were to just slide it over 60 degrees, so it was in that staggered configuration, the energy would drop by about 2.9 kcals per mole. Okay, not very much. And then if we were to rotate at 60 degrees, we're going to be at that exact same energy level. Notice that we have a total of 3 hydrogens butting up against each other 3 times. And then if we were to go back to staggered, we have that low energy condition. And if we did it again, it would just keep rotating around. We'd have staggered, and then we'd have eclipsed, and then staggered and eclipsed, and staggered and eclipsed, because the only repulsions we have are hydrogen-hydrogen repulsions. So we're going to have a fixed up high energy and a low energy, because we're pushing the same atoms past each other. Okay, so now let's get things a little more complicated, but let's draw some Newman projections for propane and butane. Okay, so propane is like that, and butane is like that. The first thing we have to do is figure out which 2 carbons we're going to draw the line down, because we have to draw a line between 2 carbons, and that's how our perspective works. So for this one right here, I'm going to draw a line here. Okay, so we're going to imagine the hydrogens are there, and we're going to draw our line on that Newman projection in that direction. So it's going to be drawn from this perspective. So this is going to be our front carbon, and then the methyl group is going to be on the back carbon. So we're going to draw our line, and let me draw the Newman projection in red down here. So I'm going to start with my middle, and my first carbon only has hydrogens on it, right? Because this is the first carbon we see, it only has hydrogens on it. Okay, so we're going to go to the second carbon, which is the one that's the ring, and it has 2 hydrogens on it, but it also has a methyl group. And I want to put that methyl group down here. When you draw your Newman projection, always draw it in the staggered configuration first, because then you can play with it after that, and it's easier. They don't all bunch together. You can see exactly which things are attached to the front and which things are attached to the back. Okay, so that's fine. So when we go for this rotation here, we're going to end up with a hydrogen methyl interaction, and then it'll be staggered again, and a hydrogen methyl, and staggered again, and hydrogen methyl. So that's how that would go around. Okay, so now for the next one, I want to draw the perspective from here down these 2 carbons. Okay, so we're going to start with that same thing. We're going to draw a dot for the middle, and the methyl group looks up to me if we're looking from this direction here. And then we have, so we're going to have a CH3 up here, a hydrogen here, and a hydrogen here. And now we have to draw our back carbon, which is the circle. And it looks like it's going down from this perspective here. So I'm going to draw it down. CH3, H, and H. Okay, so that's pretty, the method is very simple if you follow the steps. to get to this. Now we can see that we might have something different. As we rotate one of those things around, we're going to see methyl hydrogen interactions, and then we're going to see a methyl methyl interaction. Okay, so let's see what that would look like. So if we have this configuration, we actually have two possible configurations to draw these in. So the one I drew before was where the methyl groups are opposite each other. Okay, we're going to draw a ring. You're going to get lots of practice drawing Newman structures today. CH3. So when the two largest groups are opposite each other, we call that anti. Okay, because they're opposite meaning anti. And if we drew that out, that would look like that, because they would be trying to be as far apart as possible, right? Okay, the other thing we can have is, what if we rotated the back 120 degrees to put it where that hydrogen is? Okay, we're going to draw the front like we had it before. CH3, H, H. We're going to draw the back carbon. And now we're going to switch it out. So this is our CH3. This is our hydrogen, and this is our hydrogen. Okay, so now we have another name for what we're going to do here. We call this gauche. And it's the gauche configuration. Okay, it's where the staggered conformation still, but the two largest groups are within 60 degrees of each other. Okay, between the two, which do you think is higher in energy? Gauche, because the two bigger groups are closer together, right? So we have an anti is low, we have our eclipsed, which is going to be something else, and then we have our gauche. Okay, so what can we see from this is that we can actually continue drawing that around and go from our first structure, CH3, H, H, CH3, H, H. And we can draw it going one step at a time through the eclipsed. The eclipse is always harder. So you have them overlapping, and then you can keep doing that again and again until at some point in time, the CH3 and the CH3 are going to be right next to each other. Okay, and that's probably going to end up being our highest energy conformation. Okay, so when we talk about that, there's a reason that this is that, and it's called steric strain. Okay, so you have the two smaller hydrogens. They're going to come around each other. They're going to pulse each other a little bit, and then they're going to go back to stagger. Okay, so now make it 10 times larger, make it a methyl group. So now they're going to come from gauche to go and push out against each other, increasing this angle here. That's what we call steric strain. Okay, and that energy required to push them out like this and come back together for those two staggered configurations is what we call the barrier to rotation. And there's an energy value associated with that barrier of rotation, having to squeeze them out of the space they want to be in and get them around each other. So just passing two hydrogens past each other, it was 3.9 or 4 kilojoules per mole. And then by doing a methyl group past a hydrogen, so the hydrogen is still pretty small, so it only adds 2 kilojoules per mole. Okay, but when we start getting two methyl groups right next to each other in that eclipsed formation, that's 11 kilojoules per mole. And then in the gauche situation, because they've released some of that strain, they've gone from here to, they've actually dropped down to 3.8. So almost the same as two hydrogens in the eclipsed formation. So what does that mean? If we graphed this right here, we would add all those different strains together to figure out what our potential energy is. So we're going to start with 0 degrees, which is our anti-configuration. That's where the two methyl groups are farthest apart. Okay, and we're going to rotate it by 60 degrees to get to an eclipsed. When we get to that eclipsed, we have a methyl hydrogen interaction, a methyl hydrogen interaction, and a hydrogen hydrogen interaction. The total of all those interactions is 16 kilojoules per mole. Okay, so if we were to continue moving around, again, we moved 60 degrees this way, continued moving 60 degrees in this direction here, and got to this position, we're now in our gauche position. Okay, those two methyl groups are not butting up against each other, but they're closer than they were before. And so we don't have there's no interaction for these hydrogens. So this is the only interaction we have, which is at 4 kilojoules. So the difference between our gauche energy and our anti-energy is 4 kilojoules. But we haven't rotated all the way around yet. So let's rotate around another 60 degrees, and that gets us into our eclipsed. But that's the one where the methyl group is eclipsed with a methyl group. When we get to this point here, that's our highest energy, because remember, that's our highest level of repulsion. But we have to add this plus this for a total of 19 kilojoules per mole. But then if we continue rotating around, we get down to our gauche position, which is the same energy as the other gauche position, but it's not our lowest energy gap. So we have to go through one more eclipsed. You have to go through one more eclipsed and then down to our anti. And so anti is the same as the one over here. They're the same. And the two gauche are the same. And the two eclipsed with the methyl, with the one methyl group are the same. And then this is our highest energy. Do we see how that energy changes as we just keep rotating that around? And it has everything to do with having those big groups try to come past each other and try to come past each other again. Is that unsurmountable barrier? No, it's not. Heat it up to a little over room temperature, you're going to get these things to rotate this way. Okay, so that being said, what if we have more than just two groups on our system? So let's do something like right here, and we're going to look at it from the perspective of this direction here. So that means our first carbon is going to have two methyl groups on it. Our second carbon is going to have one methyl group on it. So let's draw our Newman projection. Looks like one of the methyl groups is going down, one of them is going that way, and then this is a hydrogen. CH3. Draw our back one. Looks like it's maybe going up, so we'll do a CH3 over here, and a hydrogen and a hydrogen. Does it matter where they start? No. As long as you get all the substituents in the right place, it doesn't really matter because we can rotate it around. Remember? That's fine. So in this situation here, we're going to see that we have a possibility for having two methyl groups gauche and one methyl group anti to the other one. Okay. And if we were to eclipse it, that would have a high energy, right? And then if we were to rotate it around, so let's do it where we rotate the back 120 degrees in this direction. What would happen? So let's draw the front the way it was before, CH3, H, and CH3. So we're not going to change that. And we're just going to rotate the back so there's a methyl group here. H and H. Ooh, is that a different energy than the other drawing over here? Well, here we only had the one methyl-methyl gauche interaction. Here we have two methyl-methyl gauche interactions. Which one's higher energy? This one right here is going to have the higher energy. So as you add more substituents, you have to account for each of those sets of substituents. All right, questions on that? And there's another example in the full slides on.
What would you call the one on the left?
It does not have a special name. What you would say is in this one, you have a gauche, one gauche interaction. Here you have two gauche interactions. So you'll just see that them different. Okay, so that kind of leads to the idea that, if that anti-configuration is the lowest energy configuration, then that's why we draw our things like this right here. But don't get me wrong, there's still rotation around this bond, so we could actually have some of this molecule look like this. Which one's right? As long as it has the right number of carbons, it's right. But both will exist in a bottle of heptane at any one time. In fact, there's hundreds, if not thousands, of configurations these can exist. And the only thing you need is enough energy to overcome those individual rotations. Then we can rotate around this bond, or rotate around that bond, or rotate around this bond. That's how you get thousands of these different configurations. Okay, so it's not anything about, you know, the staggered configuration is good or the anti-configuration is good. It's just you typically draw it in a zigzag structure because that's the anti structure. That's where the bigger groups are all anti to each other. All right.
How fast is that rotation now?
Depends on the temperature and depends on the barrier rotation. So the question is, how fast do the rotations happen? And in this one right here, this is going to happen slower than this one right here because it had 3 groups to interact instead of 2 groups to interact. So we're going to see that one happening faster than this one. And it might get to one and then decide to go back the other way instead of overcoming the bigger hump, you know, of the greater interaction.
So it's like swing back and forth.
Yeah, the rotation. Yes, there's a question?
Can you scroll down to the other one? Does like this rotation affect like the polarity of the interelective forces?
Nope. It does not affect the polarity because what's the net dipole of this one compared to this one? They both have the net 0 dipole. Doesn't matter what configuration it's in.
That's not gonna like weaken any of the sigma bonds either? Like,
No, the sigma bonds are held in from the intramolecular interaction between the sharing of the electrons between the 2 nuclei. And therefore they can, and because that's think about those hybridized orbitals are, you know, looking like dumbbells, they're just overlapping in the middle and they can rotate. But that's why the pi bond can't, because you have the P above and below. Yes.
So does the additional substituent affect the potential energy?
Yes. Yeah, it will be higher in potential energy than those with lower substituents. And then there'll be configurations which are even higher in energy than we'd see in the other one. Okay, so I'm going to stop here because I want to do the rings next. So we'll come back on Monday and do rings. And then on Wednesday, we'll have a quiz over chapter 4 and as much as we covered in time. Okay, any questions online? Okay, I'm going to go ahead and stop share and I'm going to stop recording.